Yeah.
Jen, I think we can start.
Okay.
Okay. So, good morning, everyone, and thank you for joining us. I'm Jian Cao, assistant professor at the University of Houston. So, on behalf of the organizing committee, I'm pleased to welcome you to the Spatial Temporal Statistics and Data Science Online series. So this series brings together professors, researchers, practitioners, and students worldwide to explore methods, theory, and applications of space-time data. Our goal is to provide an avenue to share ideas and to spark conversation that push the field forward. We are grateful for the support of the ASA section on statistics and the environment, ENVR section, the Royal Statistical Society's Environmental Statistics section, and the International Environmetrics Society tiers, whose communities have broadened the reach and impact of this series. So each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes Q&A. And please feel free to type your questions into the chat, and we will collect them and read them after the presentation during the discussion period. All talks are recorded, and the recordings along with the slides will be posted on our website. We typically host 1 to 2 seminars per month, and you are also welcome to nominate future speakers. To stay updated on the upcoming events, you can subscribe to our mailing list, and you will also find those details as well as other resources at stsds.org. Thanks.
Thank you, Jen. It's my pleasure to introduce today's speaker, Dr. Yan Song. Dr. Yan Song is an incoming assistant professor in the Department of Statistics at the University of British Columbia in Canada. She received her PhD in statistics from Renmin University of China in 2023. During her doctoral studies, she undertook research visits to Hong Kong Baptist University and King Abdullah University of Science and Technology in Saudi Arabia. She received her bachelor's in statistics from Beijing Institute of Technology in 2018. Her research interests include space-time statistics, subsampling methods, non-parametric statistics, and computational statistics with high-performance computing, with applications in climate and environmental sciences. With that, I'm happy to turn it over to Yan to begin her talk. You can share your slides.
Yeah, I'm sharing. Am I?
We don't see it, so
Oh,
maybe
really?
the next window.
So I can see shared content, but it's the videos. So I can see me twice, which is
Me too. I see
disturbing.
myself twice.
Oh, really? Why? Let me try to stop and share again. Sorry. Can we see?
Yes.
Okay. Let's see how to.
There's a hide thumbnail.
Yeah, sorry. Okay. Thank you, Mary, for the introduction. And hello, I'm Yan. Today, I'm pleased to present my research on titled Online Stochastic Generators using Slepian basis for Regional Bivariate Wind Speed Ensembles from Arrow 5. So this is a joint work with Professor Zubair Khalid and Professor Mark Jenton. So in this work, we will develop a statistical model for this regional bivariate wind speed RO5 ensembles, where this RO5 is a reanalysis data we will introduce later. So in what follows, we will first introduce the reanalysis data, the concepts and applications, and the challenges in computation and storage that motivates this work. And then we will illustrate a set of reanalysis data, which is the bivariate wind speed RO5 ensembles over the Arabian Peninsula. Will show this data illustrate the challenges. And Then we will introduce how to develop an online stochastic generator, or the OSG, to address these challenges. And finally, we will show how the proposed OSG work for the data under different situations. Okay, so reanalysis data, a type of scientific data used to study the climate change. So by assessing the scientific data, institutes and panels like the Intergovernmental Panel on Climate Change, they can evaluate the impacts of climate change and provides policy relevant insights to guide global and regional efforts in mitigation and adaptation. So scientific data include real-world observations. So they are collected directly from instruments, sensors, satellites, and weather stations. So the observations are direct measurements of climate variables. For example, here we show the precipitation data measured by the weather stations. But the observations can only reflect existing conditions or historical scenarios. Computer simulations are another type of scientific data that are generated by computers using climate models based on the physical principles, and they can reflect climate system behaviors under various scenarios. They can show future projections and the uncertainty. So for example, here we can see the temperature patterns under different conditions. But the simulations, they are limited to resolutions and accuracy due to the computational resource constraints. Reanalysis data are kind of combination of the above two data. They are generated by assimilating observations into numerical weather prediction models, or the NWP models. So by combining real-world observations with fundamental laws of physics, the reanalysis data can offer a more comprehensive, consistent, and detailed description of the Earth's climate system. Due to the unreliability occurred during the collection and integration of observations and the imperfections in the numerical weather prediction models, our reanalysis data are fundamentally uncertain. So for some of the reanalysis project, we can see that they try to quantify this uncertainty by generating multiple ensembles or multiple size of the data. Here we list several existing reanalysis projects. So here the fifth generation European Center for Medium Range Weather Forecast Reanalysis, or the ARWA-5, is quite popular in climate research. And these two reanalysis projects can provide near real-time reanalysis data, meaning that the data are continuously generated and updated. And we can obtain more recent information from this kind of near real-time reanalysis data. We can see the reanalysis data are widely used in climate research and model evaluation, weather forecast, environmental monitoring, and energy resource assessment. And they also serve as the training data for machine and deep learning based weather forecast models, especially the ARWA-5. We see that the reanalysis data are developed towards like higher spatial temporal resolutions, but it increased the demands on data generation, storage, and management. So the generation of the reanalysis data requires the support of high performance computing, or the HPC. So after the generation, the data have to be stored for future use. And the storage and management of the reanalysis data needs more advanced hardware, software, and techniques. So here we have one example. So due to the cost and computational considerations, the 10-member Arrow5 ensembles are generated at a lower spatial and temporal resolutions compared to the Arrow5 itself. So to address these challenges, statisticians have proposed stochastic generators, or the SGs. The stochastic generators are a statistical model trained on several ensembles of climate data and learning the key statistical characteristics from the data. And then we can use the stochastic generators to generate fast stochastic approximations of the training data. We call them emulations, and we hope the emulations can retain the key characteristics from the training data. We hope they can be statistically consistent to the training data. And instead of storing all the training data, we only need to store the model parameters in the stochastic generators. That's how we reduce the storage. Okay. So we can take the stochastic generator as the practical complements to the data generation mechanism and boosting their use and effectiveness. Okay, so the existing stochastic generators are actually inadequate to the reanalysis data. So most of them are developed for climate simulations with lower spatial temporal resolutions. And most of them are designed for data on the entire globe, the global data, or on a very small regional domains. But we hope the stochastic generators can be applied to any specific region on the globe. And also, most existing stochastic generators, they study the single variables, but without the consideration of interdependence between variables. And more importantly, all the existing stochastic generators can only are designed for data over a fixed time period. So for the near real-time reanalysis data, they cannot update themselves when the new data arrives. Another point is, so all of the existing stochastic generators, they may only care about to reduce the parameters to store, but they usually ignore the storage, the memory storage demands during the construction process. So if our data size is big, then the construction itself will have problem. So in this work, we proposed the online stochastic generators, or the OSGs, so which incorporates two important strategies. The first one is Slepian concentration. So the idea is to find a set of basis functions concentrate on a given region on the globe, so that we can model and emulate complex climate ensembles efficiently. The other strategy is the online updating, which allows data to enter the model sequentially in this kind of small data blocks to update the parameters in the stochastic generator. And in this way, we can reduce the storage demands during the construction, because we only need to store one data block plus some intermediate value. And also they can support near real-time emulation. Okay, so in this work, we focus on the 10-meter U and V component wind speeds from the Arrow5 ensembles over the Arabian Peninsula region. We call it ARP region. So the Arrow5 ensembles include 10 ensemble members at 0.5 spatial resolution and 3-hourly temporal resolution. They are daily updated and available up to 5 days prior to the present. So this data are actually near real time. We use Y to represent the wind speeds. So the star means the different components, different directions. And the small r represent the number of ensembles. We have 10 ensembles in total. We use capital Li, Lj to represent the grid points, the latitude, capital Li, and longitude, Lj, and we have the grid points on this ARP region. We use this small t to represent time point t after the year 2013. So we have capital T time points in total. So here we cover data of 10 years. So in total, we have 710 million data points, which takes 5.68 gigabyte. Here we show some basic statistical characteristics of our data. So here in plot A and B, we show the ensemble mean and standard deviation of the data at a fixed time point. And in C and D, we show the temporal dynamics. So here is annually, here is our 3 hourly data on 3 days. So we see that the data has a complex spatial pattern and temporal dynamics because due to the complex geographical and climate factors. We also check the skewness and kurtosis of the data. So actually our data are heavy tailed, which is very common for high temporal resolution data. It means we cannot assume the data follow some Gaussian assumptions directly. We need to use some transformation to transform the non-Gaussian data with heavy tails to be the Gaussian data. And then we can use some Gaussian assumptions that will influence our model. Okay. So now we will introduce how to develop the online stochastic generators for the near real-time data. So the idea is that we first introduce how to develop a stochastic generator using the Slepian concentration technique for data over a fixed time period. And then we will incorporate the online updating technique to develop the online stochastic generator, or the OSG, for near real-time data. So before we introduce how to develop the stochastic generator, we need to introduce the Slepian concentration. So the idea is for complex spatial temporal data, a good strategy is to find a set of basis functions and to so that we can project the spatial data at each time points to a lower dimensional space, and then we model the dependent structure at this lower dimensional space in a more efficient way. So the selection of the basis functions is very important. So in our case, remember we hope the basis functions can be data independent, because if they rely on data, we have to store the basis functions for future use of generating like emulations. And also for a given region R, we hope the basis functions can represent the data on the region well. So in summary, we hope to find a set of data-independent orthogonal basis functions such that the energy concentration in this region R is maximized. So we use G to represent this kind of basis functions. So using spherical harmonics, which we can take it as the spherical version of Fourier transform, we can represent the basis function. And then, so here the integration of the square of the basis function over the globe or over the sphere is the total energy of this basis function on the globe. So the integration over the region R represents the energy of the basis function on region R. So we maximize its energy on region R. We maximize this ratio actually represent the concentration level of the Slepian of the basis function. So finally, we can write this problem in a matrix form and get an eigen decomposition problem. So here the covariance matrix C is actually independent to data and only depends on our region R. After solving this this eigen decomposition problem, we can get our Slepian basis functions, and which are ordered according to their eigenvalues, according to their concentration levels, lambda. So here we illustrate several Slepian bases with their eigen values. So when the concentration level equals 1, we can see the basis functions, they can fully concentrate on this given region, on this ARP region. And when the lambda decrease, we can see the concentration level also decrease. And finally, when lambda equals 0, our basis function are fully concentrated on the complementary area. So in practice, we will use the first several Slepian basis functions to represent the data. So now we will use the Slepian concentration to develop a stochastic generator for data over a fixed time period. So here, remember we have Y to represent our data. And here we have data of capital R ensembles. In each ensemble, we have 2 variables. At each variable, we have a set of spatial temporal data at a fixed time period from 1 to tau 0. We assume the data include 2 parts. The first is the fixed effect. So the first step is to evaluate, store, and remove the fixed effect. So actually, the fixed effect represents the common trend of different across different ensembles. So here we can see the data from different ensembles, they look similar to each other because they share a common trend. So the first step is to remove this common trend. And now we get the remaining part, we call them random effects. So we see difference between different ensembles. We can use stochastic model to model this random effects. So in step 2, we project our random effect from spatial domain to be the Slepian domain. So instead of the spatial grid points, we have the index from 1 to capital A, and we have this, we move to this, to study the Slepian coefficients. Like here is the Slepian basis, here is the Slepian coefficients. We will model the dependence structure across these Slepian coefficients. So in step 3, remember that our data are heavy-tailed. So the Slepian coefficients are also heavy-tailed. So here for each index, we will use a Tukey H transformation to transform the heavy-tailed Slepian coefficient S to be the S tilde, which follows a standard normal. So in this transformation, we need to estimate and store 2 parameters. And equally, this gamma kappa is what we need to estimate and store. So after we Gaussianize, or after we transform the data to be standard normal, we can model the dependence structure using a simple model. So here we put the Gaussianized coefficients at all index and variables into a long vector, and we can use a vector autoregressive model of order P or this VARP to model the coefficient vector as tilde. So here we assume the vector at the current time t depends on the previous capital P times. So psi represents the residual, which follows a multivariate normal with covariance matrix K. So both the phi and K are matrices or the parameters to be estimated and stored. So finally, with all the parameters stored, we have our stochastic generators for data over a fixed time period. We can use the stochastic generators to generate emulations, and the emulation process is actually the inverse of the construction process. So we start from the vector autoregressive model. We use it to generate this S tilde, this Gaussianized coefficient, and then we use the inverse 2kh to transform this Gaussian coefficients to be the Slepian coefficients, which is heavy-tailed. And then we transform the Slepian coefficients back to the spatial data, back to the stochastic, the random effect. And finally, we add the fixed effect back to obtain our emulations. That's the emulation process. Okay. So now we will develop an online stochastic generator, or the OSG, for data arriving sequentially in time blocks. So here we consider two cases. In the first one, our data, we have a data which covers a long time period, and we can't analyze all the data at once. We can't input all the data at once. So we have to divide the data into smaller data blocks and to model them sequentially and update our OSG. In the second case is that we really have near real-time data. So the data arrives sequentially, and we update our model sequentially. So here, after each time block arrives, we can use the previous mentioned procedure or the methodology to develop a stochastic generator for this data block. So we obtain all the parameters for the stochastic generators, and we use this curly bracket to represent the estimate, the current estimates obtained directly from the current data block. And then we can use the current estimate to update the cumulative estimate, which are represented by this square bracket based on all the previous data blocks, and obtain the updated cumulative estimate based on all the existing data block. That's the idea of the online updating. So what we want to do next is to investigate how to update this cumulative estimate using the current estimates. So here is the update formulas for the step 3, where we Gaussianize the Slepian coefficients using the 2kh transformation. We have two parameters. So here we have current data block B and the corresponding current estimates. We have the cumulative estimates up to the B minus 1 block. And so here this formulas shows us a linear combination of these two estimates, and we get the updated cumulative estimate based on all the data, all the existing data. Similar for the other parameters. So here, from the Bayesian view, we can take this cumulative estimate as the prior information, and we use our data to have an update or have a combination. From the frequentist view, we can see how each data block contribute to the final cumulative estimate or the final estimate of parameters. Similar for parameters or matrices in step 4 in the vector autoregressive model is also a kind of linear combination of matrices. Okay, so here we compare the storage of the OSG and other and this FSG. This FSG is the stochastic generator trained on all the data at once. So here, so from the number of parameters to be stored, these two stochastic generators have the same number of parameters to be stored. But during the construction, we can see the OSG has a big reduction in storage demands. So here in the table, in the first one, we show the storage demands of FSG at each step during the construction. So we see the storage demands depend on the total number of time points, this capital T. So imagine if we have data covering a long time period, this T can be quite big, and the storage demands will also be big for each step. But for the OSG, if we see the storage demands in each step, so it actually depends on the length of the data block. So the tau 0 is the length of the initial data block, and the tau is the length of the subsequent data block. It will also depend on this storage demands for the cumulative estimates. So actually, it will get a big reduction of storage demands compared to the FSG. Okay, so here we apply our proposed stochastic OSGs to the data we mentioned. So remember, we have Bivariate, R5, wind speed ensembles. We have 10 ensemble members. We have data covering 10 years, and we have the data is on the ARP region, Arabian Peninsula region. We consider two scenarios. So in the first one, we have longer data blocks. So each block cover data of 1 year. So we have 10 blocks in total. So, we call it OSG long. And in the second scenario, we have data. We assume we have much shorter data blocks. So the initial data blocks cover data of 1 month, and all the subsequent data blocks cover data of 1 week. So we have much more blocks. We call it OSG short. So here we see how the parameters in OSGs update. We compare the parameters, the cumulative estimates in OSGs with the parameters in FSGs. We calculate their distance. So we can see both OSG short and OSG long. The blue and red curve can converge to 0, meaning that the cumulative estimates in the OSG can gradually converge to the parameters in FSG as we increase the data blocks. But we can notice the parameters, the estimates in OSG short have more fluctuations because in each data block we have much less data, which can cause this instability. But finally, it can still converge. That's for the parameters in Tukey H transformation. For the parameters or matrices in the vector autoregressive model, we actually can see that both of the OSG parameters cannot converge to the FSG because it lost some informations. The information is because when we estimate the current, when we obtain the current estimates, we kind of lose the first capital P time points. So the more time blocks, the more information we lost. So that's why the OSG short have a more information loss. And then we see how much storage can OSG saves. So if we see the number of parameters in OSG and we compare it with the size of the training data, we can see the OSG and FSG can save 80% storage of the training data. And if we have more ensembles of the data, we can save more. And for the storage demands during the construction, so here we illustrate the storage demands in gigabyte of FSG, OSG long, and OSG short in each step. So we can see OSG long's storage demands saves 90% of FSGs, and OSG short's storage demands saves 99% of FSGs. So for the OSG long, it makes sense because we have each data block is 10% of the total training data. Here we show the performance of the OSGs in a direct way. So we show the training data. We also show the emulations generated by different stochastic generators, and they all look similar to the training data. And the emulation process for all the data takes about 13 minutes, which is quite fast. We also use indices to compare the statistical characteristics of the emulations with those of the training data. So here we consider their uncertainty, the bivariate correlation, temporal correlation, temporal persistence, marginal distributions, ensemble mean, standard deviation, and quantiles. We give the optimal value and we show the index. So here are the results for the OSG long. The whiter the color, the better the performance. So actually from the index, they all look good. The training time for OSG long take about 28 minutes, which is also fast. If we see the OSG short, it will take about 35 minutes. It takes longer time because it needs to update more times. And here we notice for the index relevant to the relevant to the uncertainty or the bivariate or temporal correlations, the OSG short performs slightly worse than the OSG long. Remember, we have information loss when we in the vector autoregressive model, which capture the dependent structure. So it also makes sense. But in general, the OSG short also has a good performance. Okay, so in summary, we developed an online stochastic generator or OSG tailored for reanalysis data. It can update itself with new incoming data. It enabled the generation of near real-time emulations, and it reduced storage demands during the construction. And we adjust the limitations of existing global stochastic generators by allowing for regional domains on the sphere using Slepian basis. We also applied the proposed OSGs to this bivariate wind speed RO5 ensembles and validate its performance. We demonstrated the benefits of OSGs in terms of computations and storage. Okay, so I think that's all. Thank you for your patience.
Thank you so much, Yan, for the wonderful presentation. We have about 20 minutes for Q&A. If you have a question, please feel free to unmute yourself or type it in the chat. Yan Gong is raising her hand. Yan, you can unmute yourself.
Yes, thank you for the very nice talk. It's very interesting. I have a question about the correlations. So you mentioned the input data is bivariate ERA5.
Yes.
Yeah. So from this slide, you you show already like there is a bivariate correlation. So I'm curious, how did you construct like this spatial temporal correlation?
The construction can be shown here. So we can get the Slepian coefficients of both variable, this u and v components. So here, we put all of them together. So this is the Gaussianized Slepian coefficients, right? So we put all the index together. We also put all the variables together. So here in this model, we can model the dependence structure across different index and different variables. That's how we model this bivariate correlation.
So basically it's bivariate spatial temporal correlation?
Yes, yes.
Yeah, that's cool. Yeah, thank you.
Thank you.
Any other questions? I have a question.
Yeah.
What is special about Slepian basis? I mean, why did you choose that and not other basis functions?
Yeah, thank you for the question. So the Slepian basis is data independent. So like, for example, if we use like PCA to provide the basis function, the basis function are actually depend on the data itself. So we have to store the basis functions when we for generating the emulations. But for the Slepian basis, because they are independent to data, so we don't need to store them. And also if we choose the first several Slepian bases, they can represent the data on this region while not the other regions. And it's also designed for global data, for data on the region over the globe. It's not a small, not for small region.
I see. Yeah.
Thank you.
Thank you so much.
Okay.
Any other questions?
I have a question. So I wonder if you first, I wonder if there's some way to compare the ensembles generated. So I think since they are new, yeah, basically you cannot really use a RMSE or some simple measurements to measure the quality of the ensembles. And secondly, if you compare the ensembles generated by your model with others' methods.
Yeah, that's a good question. So here we can't find a unique index or a unique standard to compare. We only compare the statistical characteristics. So for example, this statistical characteristics may maybe those we care about. So we compare this characteristics. So the way is to we calculate some values from the emulations and compare it to the training data. So if we have different methods for generating the emulations, we still compare their index. So for example, here we have the index for OSG long. We also have index for OSG short. So we just compare their index.
I see. Thank you.
Thank you.
Maybe another question.
Yeah,
Here you are using the wind data side, and
yes.
I'm curious about like other variables like temperature or humidity. Does it also work? Do I need to like build a new model or like is there easier ways to adapt to your method?
Yeah, thank you for the question. So here we still need to investigate the characteristics of the data. So I think for temperature, it can be similar, but for the precipitation, this can be different. I think we still need to develop the model based on the characteristics of the data itself.
Like a new set of the basis function, or like a
No. So for the basis functions are the same, the Slepian coefficients, the Slepian basis, because they only depends on the region information, right? It's not relevant to the data itself. So we can still use the same set of Slepian basis. But for the modeling of the Slepian coefficients, the dependent structure, it may be different. Yeah.
Thank you.
Thank you.
Any other questions? Do you have a package for this, Ian? Or
The package.
Or yeah, can we try the online stochastic generators?
Yeah, you can try. Like, yeah, I have a GitHub link, but it's not on the archive. Sorry, but if you want, I can share.
Okay. So if there are no more questions, then I think we can end this session. If you have other questions, you can ask Yan Song via email. We will send announcements for our next speaker. It will be next month. So I hope you stay tuned. Well, thank you so much.
Yeah, thank you.
Thank you, Yan.
Thank you.
Thank you.
See you. Have a good day.
Thank you very much, Yang.
Yeah.